Can I serve water? Of all the people, you cannot. As much as I know you in half a year, you cannot. I know you, your mind is always, it's always switched on. There's no off. Yeah, but I always tell you to take a break, but now I've stopped talking. I know. Okay. Seriously, what can I say? Okay, fine. I tried. How can you say like? No, that's why I say you and Karan are very similar. He's also one. But you cannot say something like, okay, I don't care about tomorrow. I will live tomorrow. I'm telling you to take a break. Not forget about it, just take a break.
Hi.
Okay.
All systems are go. Yeah, technical systems are go. Now contents. Multi-body dynamics, right? Yeah. Okay.
Remember
To remember. Thank you very much, officer. And the live stream on it. Great. Thank you.
As soon as we understood the lecture. I was on your mind. Huh? Maybe you have 50 minutes of class, 10 minutes of break, and whenever you want, you can just raise your hand and go to talk. We respect our privacy, so we cannot. Yeah, you have to. You just cannot leave like that. You have to leave. If you want to drink water, there are few professors who you want to ask permission to drink water. May I drink my water? Okay, no. But now it's changing. Now it's asking how do we select? Just laugh. Oh shit.
Yeah, great. Oh, it's better to close. If you pull it sideways, no, the cord. No, not the other cord. Yeah. And then let go. Yes, thank you. And the same applies there. Okay, yeah, I have to press a button. Oh, it's already recording. Cool. So that is recording, that is streaming. And then we start here. Yeah. Welcome to the third lecture on multibody dynamics. All systems are go. Is anybody in the live stream now and sees that it's working? Can I see a hand? Yeah, thank you. It's just for me to check that things are up and running. Today's topic is systematic approach. If you have done the homework, you will have discovered that you have drawn these nice free body diagrams and wrote down the constraints, but actually there you have done some work twice, it looks, if you look closely at it. And we'll see what happens and if it's there an easier way to get your equation of motion. But of course, first we're going to do the in-class quiz. Huh? And I took your comments and remarks from last week about fonts and too much text and those kind of things, so I tried to improve it. The major improvement is that my talking head is now not on the bottom right but on the top left corner, and hopefully not obstructing the correct answer. That was sort of stupid. Okay, let's see, where are we? Of course, logging in. Okay, let me repeat it again. If you use a username, if you want to have credits for the in-class quiz, in your username should be your student ID and no comma. And no offensive names, but that's clear. Ja, dan gaan we naar Kahoot. My Kahoot. Number 3. Okay, loading. Classic. Oh. Het sound is off. Yeah, please log in. Oh, I should screen, right? Oh, I don't know. It's okay. Well, it looks like there's some saturation going on here. We have some limit number almost per. Oh, wow. Oh, gone again. Yeah. I'm sort of happy. So let's start, right? Nice new banner. This is about Greek letters. And then apparently who is who? We all know the game, right? Who is who?
Yeah, it depends if you want to say it on
Oh, so it's English pronunciation. Yeah, it's not Dutch or Greek.
I press it wrong. Instead of pressing C, C, I press C. You'll get 6 or 8. Doesn't matter. Bonus I
I'm really happy with the result. And I put the question because sometimes I have a student who comes to an office hours and then says, yeah, this angle theta, and then he's pointing at a symbol. I think that's not theta, that's phi. So therefore I put the question. But class, you're wonderful. There's no problem here. Our Greek is top. Okay. Last week, this question did not score so well. So I thought, well, let's give you a second chance, right? It's the identical questions, but the answers are not identical to last week, so be aware. The correct answer is there. Now a cheater is starting the recording, right? Take your time, you have enough time. We still have more than a minute. So just calculate.
Yeah, this yes.
No, you can check all the options. If you can mark correct. Name, right? We got Dragon.
Yeah.
What did you get?
Wise monkey, something like that. There were so many.
We were talking about physics.
Okay, no problem there. Most of you are up to speed with the mass mode of inertia, right?
What is Karan?
Where's Karan? Oh yeah, there you are. Great. I should put a little more effort. Huh? Okay, determine the number of rigid bodies, the number of revolute joints, and the number of degrees of freedom for the following mechanism. And it's clearly the sticks are the rigid bodies, and where you see a circle, there's apparently a revolute joint.
Number of degrees of freedom is the number of levels in which you can select the
Staat overal 6. Dus,
Ja, nee, daarom.
ik kan alleen maar 6 kiezen. Dus, wat ik ze kiezen.
die ene Ja.
And the last one is related to the other two.
Okay. Let me show the media first, right? So apparently something went wrong. Either I put the wrong answer in as a correct answer, or you have the wrong answer, right? We can ask Karan, of course. Is the correct answer the correct answer? Oh, you don't think so? Okay, cool. Okay, let's look at the picture. Yeah. Well, how many rigid bodies? Well, there was only one choice, right? You could say 6. But all answers had 6. 1, 2, 3, 4, 5, 6. Yes, 6 rigid bodies. That's clear. But then, if we look at the options we have for the revolute joints, it's either 7 or 8. So let's look at the picture. Well, this is clearly between this body and the ground, one revolute joint, right? Between this body and this body, one revolute joint, right? Between this body and this body, one revolute joint. This and this one, this and this one. But now, between this body and you can either pick this one or this one, is also a revolute joint. Yeah? So, you really have to think, oh, if I have to build this thing, what do I need? What is the hardware I need? So, you need hardware between this and this body, or you could connect it to this one. Well, when I look at the picture, it's apparently this one is with a revolute joint to this one. So this you have times 2. Again here 1 and here 1. So 8, yeah? 8 revolute joints. So that was the option, either 7 or 8. Now get back to the number of degrees of freedom. To be honest, I always do like this. I have a sort of a mechanical intuition, like, oh, if I move this, then that moves, and then that can move, and it does not always work. What does work is just doing the math. 6 times 3 minus 2 times 8 ends up in 2. Right? Okay, so this was really a learning curve. Geen idee?
Sorry, I didn't really get how you...
The last sentence, yeah. 6 rigid bodies. Every rigid body has 3 degrees of freedom. So in total we have, as free bodies, 3 times 6, 18 degrees of freedom. If they're all free floating. But they're not free floating, we have 8 revolute joints. And every revolute joint has 2 constraints. And 2 times 8 is 16. 18 minus 16 makes 2. Okay, next question. Here I want to know what are the velocities on the mechanism. So on the left side you see a mechanism with all kinds of constraints, dimensions, and one angular speed given of the lower bar. And then to start my whole calculation, I have to know what are the speeds of the center of mass, horizontal, vertical, what is the angular speed. Yeah, pretty good result. Still, on average, what is it? 70 something people have to brush up their kinematics, but that's not so hard, right? Okay. The last question. So when you did homework 1, you got this matrix, and then the question is, you have this upper part A and lower part B, and is there a relation, yes or no, and what is it? And I don't know. No clue.
Yeah, I didn't do, but it should be. I did. It's alright.
No, no, guys, it's a steep class. It's class. Because I did it for steep class. Now?
Now do whatever you can. It's either orange or smell. I didn't. It's not on. I think it's blue. Because I remember something like that. No, minus.
So there were 2 correct answers. I mean, it all depended on how you formulated your constraints, with a plus or a minus, or what your choice was of a sign for the constraints. So both answers, I would say orange, but I'm colorblind, so it could be anything. And blue, I sort of see. So those 2 answers are correct, depending on how you formulate the question. But the basic thing is the transpose. One matrix is sort of the transpose of the other one. And actually today, during the lecture, we will see where that comes from. Because it means that if you have derived the equation of motion and you separately derive B and A, then you did too much work. Now there's one thing in life we don't want to do. Too much work. So we will seek for the method where we don't have to do that. Do not have to do it. Okay. Now we have to wrap up. Yeah, I'm going to get the results. Is Nidar in the room? No. Well, eternal fame. Please give feedback. I appreciate that. That's really helpful. And it's just one press or something like that. Okay. Well, I'm happy to see this because I remember from last week I was in the 3.6 or 3.8 for the feeling, the satisfaction, and the learning I don't remember. So things have improved apparently. Thank you. Is there anything else here? No, I think we're done with the Kahoot. In-class quizzes, I can come back to that. So now we go to contents. Yeah. Yeah. Let me check one thing. Yeah, it's still working. That's good. Yeah. Okay. So. Yeah. Okay. Finished. Should I wait? Okay. So before we do the systematic approach, let's look at the results we got in our homework assignment, the things we calculated. And I take the case where the both bars are vertically up and there's no initial speed. So I say let's look at results homework 1. So I want to look at this case where they are vertically up, and this is then the constraint. This was body 1, this was body 2, there was this field of gravity. Yeah. No, we should put coordinates here with x, and here we have the y, and the phi is alright in this direction. Then the results I got, and hopefully they comply with your results, because otherwise I did something wrong, right? Phi double dot 1, x double dot 2, y double dot 2. Phi double dot 2 equals, oh yeah, and the loading is just gravity, yeah? So this is m2g and this is m1g. The results are 6.36, 0, minus 25.2, that's a big number, 10.5, 1, 0, and 8.41. Okay, now why do I do, what are the units? So accelerations are in meters second squared, right? And this one too. And this is in radians second squared. And that immediately explains why this is such a large number, right? So apparently radians are large things opposed to dimensions here. One full circle is already 6 something in the order of 10, whereas the length scale of this is 1 or approximately even less, if I remember. Where the bars were like 75 centimeters or 50 even. So if you compare that length scale to the length scale of radians, there's this order of 10 something, and which we see in the answer. Okay. The zeros. Are we happy with the zeros? So is there no acceleration in the vertical direction? Can there never be an acceleration in the vertical direction? When?
When it's falling back or on the side table.
But it's already falling.
Next time instead.
No, when it's opposite. When I put it opposite.
Yeah.
We will have forces in the vertical direction only.
Will there be accelerations in the vertical direction if we have forces there?
If we have angular velocities to the...
Yes, I was looking for that. When there is an initial velocity, and especially an angular velocity, then of course some parts, and especially we know this part, will move in a circular arc. And even when it has a constant velocity, but when it moves in a circular arc, it has an acceleration, because although the velocity in magnitude is constant, the direction is not. And so you have to change the direction of that velocity, and we call a change of velocity an acceleration. And we know already immediately, if this is then the speed, constant speed, then the acceleration should be downward, centrifugal. But there are no initial velocities here, so there is no acceleration in the vertical direction. So I'm happy with those numbers. So if there's a non-zero velocity, you would expect numbers here, right? Next, what can we say? The signs, are they according to what we expect? So if there's a force, force pulling my notes away. If there's a force pulling in this direction, then we expect the thing to move in the positive x direction. Newton says sum of the forces mass times acceleration. He doesn't say sum of the forces minus the mass times acceleration. He could have said that. Would have been clumsy, but could have been a law. So we expect if you push something in a direction, it will move in that direction. And yes, that's what we see. It moves and this moves. Now the angular accelerations, I have no clue actually. I have trouble because there's this different length scale. Apparently this is falling, one is falling in the negative direction, that is okay, so that's in this direction. But 2 is positive, so that's apparently, I'm doing like this. So 1 is like this and 2 is like that. No, for the camera it goes all wrong. Forget it, I didn't do that. Mirrored it. Anyway. So this is difficult. So that we put that on the stack later on. Now there's another number which makes give me a big concern. Does anybody know which number that is? I have one result where I think this can't be true. Any idea which it is?
10.5.
Yeah, 10.5. I heard that, and you wanted to say 10.5, I bet, and you said it. Great. Yeah, this number. And why? Because it's larger than the acceleration of gravity. So, wow, we have designed a machine which in a field of gravity can fall faster than gravity. I should say it correctly, can accelerate faster than the acceleration of gravity. That's pretty cool. So, is that really true, or did I make a calculation error?
Because of the actual force.
Well, before we do reasoning, let's do democracy. Is it true, according to the rules of democracy? Yeah, can I see hands? Yeah, okay, well, democracy, I should turn the camera, which I didn't, but I see a lot of hands going up. Democracy tells us that it's correct. So something is apparently in this system that makes this body, and apparently body 2, fall faster than gravity. Now, there's only one way to go faster than gravity, and that is by applying a force. So apparently there must be some magical force applied to body 2. Exactly, that's the joint force, the force in the joint. So through reasoning we come to the conclusion that body 1 is pushing body 2. But we can check that, because we have that in our results. If we look at the constraint forces we calculated, then these were the FCs, according to my system, VA, HB, and VB. These numbers were, I don't know, those are incorrect, but it doesn't matter, it's more about the sign. 0.10. Now looking at these numbers, we see that B is a positive number. Then we have to go back to our sign convention, and if I remember well, then our sign convention was like this. If this was body 2, then this was HB. And here we had M2G. So if HB is a positive number and it's acting like this, then yes, of course, I would expect to have x double dot 2 to be larger than the acceleration of gravity. Yeah. Still remains how, yeah. Yeah, question.
Yeah, about what type of what is the equation for the inertia? Because when I compare my results with the presented, it is similar, but they're not equal. I mean, for the third one, I get 2.22 minus 22, and I don't know if I make a mistake on the inertia or not.
Since we are with more people than you here, this is really fit for office hours and not for the lectures, okay? So maybe I made an error there. Yeah? Is that a big difference?
There's one is the same, 10.51,
Yeah.
but the other are not the same.
Okay, well, you're probably right. In fact, according to democracy, I mean, these are notes from I don't know how many years ago, so probably I copied the wrong one. Yeah, probably. But, okay, yeah, different dimensions. I think even, different dimensions, that was the case. Mea culpa, sorry for that. You are right. Still, the thing remains, I mean, in your results and in my results, that this one bar is pushing the other bar and there's a positive force, and how does that go? Well, to investigate how that goes, you can actually have to cut the bodies loose. So why does it fall? Why is 1 pushing 2? Then we could cut them loose. We say, well, we have this one body that apparently, if it was a free body, it would go with gravity. And then the other system we have this pendulum here at a hinge. And also here we have gravity, mass, and here some mass and some mass moment of inertia. And then the big question is, of course, what is the acceleration of this point, A, and then we call that B. If the acceleration of point B is larger than gravity, then it's okay. Then yes, then body 1 will be pushing body 2. Now, how do we determine the acceleration? Can we determine from this problem what the acceleration of point A is? This was point B, sorry, this is point B. Yeah. Yeah, we have, of course, we have our Newton-Euler equation. So formally, officially, I would have to write down all the 3 equations of motion together with the 2 constraints and then solve the system. Do you agree? Yeah. However, there's a shortcut here, and the shortcut is that the joint here is fixed in inertial space, and the Euler law holds for a number of cases. The case where you say sum of the torques about the center of mass is mass moment of inertia times the angular acceleration, but it also applies for a fixed point of the body. So if there's one body which is fixed, you can say fixed in inertia space, the point, not the rotation. Then you can say, the sum of the torques is mass moment of inertia times angular acceleration. So we can write here the adapted Euler equation, sum of the torques about A is mass moment of inertia about A times angular acceleration. And then these were the signs I choose, the angular acceleration. The thing has a length L, and now we're going to do everything right with it's a slender body. First the sum of the torques. The sum of the torques is easy. That's the force. And let's say this is positive in the direction. And then it's the length over 2, right? That's a torque. No more torques. And then the mass moment of inertia. I know by head that this is something like this. 1/3 ml squared. because at the center of mass it's 1/12, and then you have to put that out of the center of mass with a distance 1/2 L, and you have to take the square of that. You get 1/4, and they go 3/4 into 1/12. So 3/12 plus 1/12 is 4/12. That's 1/3. Yeah? Times the angular acceleration. From which we conclude, well, this goes away, and this goes away, and this goes away. So the angular acceleration is... What is it? 3/2 g/L. That's not our answer, because we didn't want to know that, but we wanted to know what is the acceleration of point B. And that is, of course, the angular acceleration times the length of the bar, and that then becomes 3. And that's larger than gravity. So yes, point A is accelerating with a larger acceleration than the acceleration of gravity. So apparently body 1 is able to push body 2. And that also explains that when the thing is falling, and now I will do it correctly, when the thing is falling, this will happen. This will happen. And then more things, which I don't know. Okay, why are we doing this? Why are we here? Well, we are here because we want to know this one. Why are we here? This is the thing we want to know. We want to know, how does the system move in time? Now, did we calculate that with homework assignment 1? No way. Can we calculate that? Yeah, we can, we just integrate. So how do we find the motion? I think it's super simple. If you have you want to know the new position, right? So you say x new is x old plus, well, if I drive 100 kilometers per hour and to Utrecht is 50 kilometers, I know how long, speed times time, right? Then I know my distance. So delta t or something like this. Super simple. But the state of the system is, of course, not only the position. The state is the position and the velocity. And from that state, with the equations of motion, we find the accelerations. So not only do we have to determine what is the position, but we also have to know the speeds. So the new speeds, well, actually it's the same formula plus times the accelerations. And these are vectors, right? This is what we call the intuitive method, and the intuitive method is based on intuitive method. Any idea? No, a deeper thing. And so, what is the background that you're allowed to? Where does this formula come from? It's like I pulled it out of space. Like, oh, here I have a formula. Or I take my BINAS. I don't know how to translate BINAS. BINAS. I take my BINAS and then I look it up. Oh. Actually, it has, of course, a clear mathematical background, and that is within the definition of speed. Because if we take the definition of speed, then that's defined as the limit case of delta t going to 0 of, and then we say xt plus delta t minus xt, and we divide that by delta t. Now, we can fiddle a little bit around with all these symbols, so what we want to know is this guy, right? The new position, and we have the old position, and we know the step we want to make, and we know what the speed is. So we just turn it around and then we say, oh yeah, the xt plus delta t is equals to xt plus delta t times x dot. So that is really the basis for doing these approaches. There's one but, because what did I omit? The
Acceleration the position should not include x double dot times change this.
Oh, the velocity. Yeah, no, I can write that sentence down too. But let's focus on the position. Yeah. Yeah, even in a mathematical sense, where did this thing go? Limit delta t to 0. That's not here. That's lost. So where shall I write that? Well, if I write it before the whole sentence and delta t goes to 0, I get xt equals xt. Ah, that's helpful. That's really, yeah, that's going to work. So we made an approximation. We instead of delta t going to 0, we have delta t is finite. It's small, of course, but it's finite. And why do I say it's small? Because officially, when you write this down, you should have written plus delta t squared times x double dot. Oh, that's ugly. Come on, man. Real ugly. X double dot plus, and there should be in half, plus 1 over 3 delta t to the power 3x triple dot plus da-da-da-da, etc. So you have this whole expansion in delta t. But we do an approximation. If we take delta t small, we can do an approximation. And then we can say, oh yeah, the nu, the t plus delta t equals to this one plus delta t times the speed. And then we usually say plus order delta t squared. And we write this to make you aware, oh, you shouldn't pick the delta t too large. Or for a mathematical person, this is a first order scheme. No, this should be a t. Yeah. But of course you can expand that, and in our case we could expand this easily because we can easily add this term, a 1/2 delta t squared x double dot, because we have the x double dot. So we can even make our position more accurate than our velocity approximation. We could. So that's a little bit about how you do that. And now I like to spend the last couple of minutes on calculating that position. And of course I'm going to use the wrong numbers. Well, not your numbers. Oh yeah, I see. Ah, stupid me. Yeah. Ah, yes. Really old notes. What I've been doing. Well, we can solve that. Now, this was 2,9. Yeah. Yeah. Oh, let's get rid of everything. Now see if we agree. 0 minus 22.89, 10.59, 0, 7.57. Are we now more on speaking terms? Yeah? Okay. The forces, I don't know, it all depends. Yeah, it depends on what material, and I change the material every year. I don't know. Anyway, yeah, last part. So let's go back to the numbers. Let's do this whole game of integration, of finding the motion. So meaning we have here the position x1, y1, phi1, dot, x2, y2, and phi2. But not only do we have those, but we also have the velocities, right? So we have x dot 1, y dot 1, phi dot 1, x dot 2, y dot 2, y dot 2. And of course, we also have the accelerations. X double dot 2, Y double dot 2, Y double dot 2. Oh, this should be a 1, sorry. And this is a 2. And this is a 2. Ta-da, ta-da. Okay, now we put in the numbers. So this is t is 0, right? Now, I do know what the speeds were. They were all 0. That was easy. And then the position was the length of the bar was at 55 millimeters. Yeah. Okay. Okay. Well, in the initial position, the x was 0, the y was the half of the length, 0.275. Then the angle, it's upright, so that's pi over 2. Then again 0, because it's upright. And then, yeah, this is difficult, 0.55 added with the other one, so 1.5 times 55. And again upright. So these were the positions, those were the velocities. Then the accelerations, well, approximately 6.30 minus 22. I mean, we're doing numerical integration, so that's approximate anyway. Yeah? Okay, the first step. So now I want to calculate at a new time, moment in time, and what time step shall we take? 0, 1. Why not 10?
It's too large.
Too large, eh? And why not 0.00165438? Yeah, make life hard. So just for demonstration purpose, I take 0.1. Because we have this decimal system. Okay, so what do I have to do? Well, the new position is the old position plus the time step times the speed. So that's not so hard. I can do that. While doing this, I have the feeling I'm doing something stupid. So the thing is not moving? We have the position in this time step, and then one time period later, it's still in the same position. So nothing is happening. Can somebody explain? Yeah. It's building up. I don't know about building up speed, but I know that it has a speed of 0. So when you have a speed of 0, how much will you move? 0. That's all in the definition. I mean, if I say I'm at rest, then I'm not moving. So it's pretty logic that you say, well, we're still in the same position. Houston, we did not move. Yeah, that's life. Okay. Yeah, question.
Shall we use the acceleration instead of the velocity, at least for the first step?
Should I not?
Shall we use the acceleration instead of velocity, at least for the first step?
I don't know. I have these formulas. I'm sort of stupid. So it says new position, old plus speed times delta t. That's what I have. What else shall we do? Okay. Apparently, well, I see no error here yet. Let's move on. So apparently we're still in the same position, but now we do the new velocities. Now the new velocities are the old velocities plus the acceleration times the time step. Aha! Now I'm in business. Because although this is 0, this is non-zero. So this is going to be 0.63. This is going to be 0. This is going to be minus 2.3. 1.1. 0. 0.76. Aha! So what have I established? I've seen it's still in the same position, but it has picked up speed. And that's exactly what's in the definition. It has a zero velocity, but it has a non-zero acceleration. And acceleration means change in speed. It doesn't mean change in position. Yeah. So now we have a new position, new speed. We put that in our equation of motion machine, and we turn the handle, and then we get a new acceleration. And new acceleration is approximately identical to this one. Why do I say that? Because I'm lazy and I don't want to calculate the new one. And I know it hasn't really moved. So, should be about right. The only error which happens is, of course, we have now finite speeds, so these numbers are probably not right. We have now angular speeds, and then we get probably wide vertical accelerations. Small ones, but you can check in your calculation if that's true. But for now, it's okay. Next step. Okay, new position. Again, new time step. T is 0.2. We do the same thing. We take this position times this number times this. And what do we get? We get here 0.063. We get here nothing changes, 275. And we get the next one. Oh, help. Minus, no. Oh, I'm not good at this. A 1, a 3, and a 4? Something like that, eh? 0.11 is the same, and 1.646, etc. So we see it's slowly picking up, the position is slowly changing. We see, by the way, a quadratic contribution of the acceleration, delta t times squared comes in here. Speed is picking up, we don't see here. Now what is the motion? I can show the motion, hopefully. Yeah. Be patient, lecture 3. Oh, here you see the motion. Yeah.
For x1, why is it 0.003 and not 0.006?
For x1, it's 0.063. That's a 6.
Oh.
Yeah, my handwriting is really not to write home about. It's unfortunate that I can't do it larger. No, yeah, anyway. Doesn't really help. Anyway, this is the motion, and we see what we expected, that this bar is moving like that and the other one is like that. But what we also see is that the things are flying apart. That's not good. Why are the things flying apart? Well, you get a gap here, yeah. Okay, let's do a break, and then I'll make sure after the break that the video just runs. Sorry for that.
Yeah.